Good morning, afternoon, and evening, everyone. I'm Zhiyuan Liu from the Natural Language Processing Group at Tsinghua University. It is my great honor to have this chance to give the talk here. Our works mainly focus on natural language processing and knowledge graphs, and the topic of this talk is knowledgeable pre-trained language models. Human language is closely related to human intelligence. Natural language processing has been studied for about 70 years as a core of artificial intelligence. It is a key to parsing Turing test and realizing artificial intelligence. For human beings, we require lots of knowledge to understand complex semantics at different levels. For example, given the sentence, Tom coughs today and may get infected by COVID-19. With different knowledge, we can capture different information from the sentence and give different responses. Hence, it is not easy for machines to understand human natural language. It requires a machine to have the ability of knowledge acquisition, representation, and application. Looking back at the research spectrum of natural language processing, to some extent, we are always studying how to make machines obtain all kinds of knowledge for language understanding. In the early stage of artificial intelligence and natural language processing, people tried to manually design rules for language understanding, such as linguistic rules in grammar theory and knowledge bases in expert systems. This symbolic knowledge is usually human-friendly, discrete, and sparse. As symbolic grammar rules and knowledge bases have critical issues of generalization and coverage, statistical machine learning methods have been widely applied to natural language processing after the 1990s. The statistical methods can learn complicated language patterns from data. The learned models contain rich knowledge for specific natural language processing tasks. We can actually regard the learned patterns in machine learning models as a form of knowledge for language understanding, named as model knowledge. As compared to the human-friendly symbolic knowledge, the machine-friendly model knowledge usually has better generalization. In recent 10 years, neural networks have been introduced to natural language processing. As compared to statistical machine learning, deep neural models are more expressive due to distributed representation and deep architecture. These neural models can also be regarded as powerful tools for building model knowledge. In summary, the research spectrum of natural language processing is about knowledge acquisition, representation, and application for language understanding. This is also the reason we propose the framework of knowledgeable learning for natural language processing. Various types and forms of knowledge have been explored in history. It seems that model knowledge is currently the most effective form for language understanding. As we have shown, we argue that knowledge is the core of language understanding. There is a closed loop of knowledge in natural language processing. First, we learn to extract and summarize structured knowledge from noisy text data. That is knowledge acquisition. The main challenge is how to extract accurate knowledge from large-scale noisy data. In recent years, various efforts have been devoted to this part. Second, we will represent the symbolic knowledge in a machine-friendly form, that is knowledge representation. Last, this existing knowledge should be used to guide and improve the learning process of natural language processing systems. This is also the focus of this talk, knowledgeable learning of pre-trained language models. That is how to incorporate existing knowledge into deep learning framework. As compared to conventional deep learning methods that only learn from supervised data, pre-trained language models can take advantages of large-scale unlabeled data to capture rich knowledge about language understanding. Recent experimental results have shown that pretrained language models can achieve state-of-the-art performance on various natural language processing tasks by fine-tuning their parameters. Pretrained language models can be regarded as the most advanced approach for building model knowledge. However, original pretrained language models can only learn from data. In fact, many background knowledge is also required for language understanding. For example, the facts of Bob Dylan in knowledge graphs will be helpful for the understanding of this sentence. Hence, given the rich symbolic knowledge accumulated by humans, it is important for pretrained language models to learn from both data and existing symbolic knowledge. Some works have been done to incorporate symbolic knowledge into pretrained language models. In this talk, we summarize these works into 3 approaches. The first approach is knowledge augmentation that aims to extend model input with external knowledge according to the entities or concepts in the sentences. The second approach is knowledge regularization that aims to design additional pre-training tasks with the help of existing knowledge to regularize the learning objectives of pre-trained language models. The third approach is knowledge framework that aims to take advantages of external knowledge to prune the architecture of neural models. For knowledge augmentation, a representative work is ERNIE, published on ACL 2019. Considering external entity knowledge can benefit language understanding of low-resource entities, ERNIE is proposed to encode both text sequences and entity sequences as input, where entity sequences are formed by entity embeddings in knowledge graphs. Specifically, the lower layer of ERNIE are designed for text, and the higher layers are designed for knowledge integration. Link prediction is also proposed as an additional pre-training task for knowledge integration. Experimental results on entity typing and relation extraction show that ERNIE can better encode external knowledge of entities for text understanding and improve the performance of entity-rich tasks. This also verifies the effectiveness of incorporating knowledge into pre-trained language models. Another representative work of knowledge augmentation is KeyBERT, published on AAAI 2020. This work also aims to enhance language representation with knowledge graphs. KeyBERT adds the attribute triples of entities into the input sequence for pre-trained language models. As shown in the right figure, the augmented text has a hierarchical tree structure. To better explore the complicated structure, KeyBERT also designs specific attention masks for relations between entities, as shown in the left figure. For knowledge regularization, we select Kepler as an example. In this work, we use entity descriptions in knowledge graphs as a bridge between language models and knowledge structures, and jointly learn mask language modeling and knowledge embedding as a unified model. Specifically, we design a pre-training task for knowledge embedding, in which entity embeddings are encoded according to entity descriptions. Following the setting of structured knowledge embedding, the relation is modeled as a translation from head entity to tail entity. In this way, we can take the structural knowledge in knowledge graphs to provide additional and informative signals for language models. Experimental results show that Kepler can achieve better performance than Robota on those tasks requiring entity mention understanding. Another example of knowledge regularization is CoreRefBERT. This work explores knowledge regularization provided by co-reference in discourse. Co-reference is a phenomenon that two or more expressions in a text refer to the same entity. For example, sentence, the book refers to the Little Prince. Co-ref-BERT aims to learn co-referential reasoning from large-scale unlabeled corpus. Specifically, it masks one or several entity mentions and requires the model to predict the masked mentions corresponding reference. After incorporating co-reference knowledge into pre-trained language models, co-ref-BERT can achieve better performance on those related tasks, such as question answering. For knowledge framework, K-adapter injects multiple kinds of knowledge by training adapters independently on different pre-training tasks. Different from conventional multitask learning for knowledge integration, K-adapter fixes the original pre-trained language models. For each new kind of knowledge, K-adapter will initialize a new adapter network and concatenate the outputs of both original pre-trained language models and adapters to make prediction. Another example of knowledge framework is KGLM. It modifies the process of language models with external factual knowledge. The work first conducts entity linking and maintains a localized knowledge graph containing facts that are possibly mentioned in the sentence. Then, KGLM will predict next word with mechanisms for selecting and copying facts from knowledge graph. As shown in the right figure, the model first decides the types of next word, maybe an entity related to existing entities, maybe a mention of a new entity, or simply a new word. If it is the first type, we will select an entity from the local knowledge graph. In this way, the learned language model can take advantages of external knowledge graphs in language modeling. Recently, GPT-3 achieves an awesome performance by leveraging a natural language prompt. Prompt tuning applies closed-style tasks to bridge the gap of input forms in pre-training and fine-tuning, providing a promising direction to better stimulate model knowledge of pre-trained language models. Since composing natural prompts is not easy, some recent efforts explore auto-generated prompts or soft prompting. It is important and interesting to incorporate task and domain knowledge into prompt tuning, including prompt design and tuning instances. In summary, there are in fact two forms of knowledge for language understanding: symbolic knowledge and model knowledge. These two kinds of knowledge can be converted to each other. A typical machine learning framework, including pre-trained language models, is composed of four parts: input, model architecture, objectives, and parameters. Various approaches, as mentioned in this talk, have been explored to incorporating knowledge into these components. Okay, that's all for knowledgeable pre-trained language models. With the help of knowledge acquisition and representation, we can effectively apply the knowledge to guide the learning process of natural language processing systems by knowledge augmentation, knowledge regularization, knowledge framework, and knowledge transfer. The future natural language processing systems should be able to learn from both data and existing symbolic knowledge. In future, there are still many open problems for knowledge acquisition, knowledge representation, and knowledgeable learning. And the ultimate goal is to realize knowledgeable and interpretable natural language processing. Currently, it is a feasible solution to integrate various knowledge in a large-scale pre-trained language models, and then stimulate the model knowledge by prompt tuning. That's all for this talk. You can visit my homepage to find more information about this talk. Thanks.